Our first speaker today is Antonio Mezzacapo from IBM, telling us about quantum simulations of chemistry and lattice models.
All right, thanks. Is this working? Thanks. Yeah, thanks. All right, thanks, Alireza, for the introduction. I'd like to start with some motivation why we're doing this. Chemical reactions are very important, and they are the basis of many drug and materials discovery. And our understanding of how these reactions, like the way they happen, and our ability to design new materials and new drugs is fundamental for progress to make progress in our society. So we would like to understand how they happen, and we would like to characterize them. So how do we do that? Typically, the information that we need to predict is the energy that that is dissipated during a certain reaction, right? So typically, we have some reactants, and with an initial energy configuration, they undergo some transition state, and they get to the final product energy. And so we would like to understand, we would like to compute these energies because the reaction rates are directly related to these energy differences. And this is the energy of steady states, ground states of these systems. So understanding chemistry, okay, now it's working. Understanding chemistry becomes a problem of ground states. So we want to compute the ground states of these molecular systems, and we want to compute their energies. Okay, and so we want to do that with quantum computers. Arguably, this is the best use of quantum computers. Probably the most direct use of quantum computers is to use them to simulate nature, because nature is quantum mechanical. And specifically, we're interested in ground states, right? So now, there is a well-established, famous quantum phase estimation algorithm that addresses this problem, and it does so with some convergence guarantees, right? So if you start with the reference state that has a polynomial overlap with the target ground state that you're interested in, then quantum phase estimation, it's a polynomially efficient algorithm. We'll give you the solution. The issue with quantum phase estimation is that we cannot run this algorithm for realistic chemistry systems on the quantum computers that we have today. So the depths required to run quantum phase estimation with errors that are small enough. They're prohibitive for the quantum hardware that we have right now. And so what people have thought of alternative ways of targeting the ground state problems on pre-fault tolerant quantum computers, and the most infamous one is the variational quantum algorithm that we at IBM started to work on, I think more than a decade ago at this point. The VQE or VQAs are ways of going around the step problem, because what happens is that we can test the goodness of a short depth quantum circuit in approximating a target ground state. And we do that variationally. So we estimate the molecular energy cost function, and we try to optimize a parameterized short depth quantum circuit to try to get it to capture our ground state, molecular ground state. Well, the issue with VQEs and VQAs is that, first of all, we were not sure about the quality of that ansatz. So there is an ansatz design problem. And also there is the equally infamous measurement problem, right? So these molecules are very big. The number of measurements that we need to capture their molecular energies is prohibitive with the current quantum runtime that we have for even for superconducting processors, which are the fastest ones. Okay, so it seems it's not getting us to large system sizes, VQE. So this is a plot of problem size on the y-axis, so the qubit count for given molecular problems as a function of the year. And so you see that basically in the last decade, there hasn't been a lot of progress in terms of scaling up these algorithms to large system sizes. And so it really seems that VQEs have reached some kind of wall for when we try to scale this algorithm up to large system size. Okay, and so let me give some numbers behind these statements. Okay, so take this iron sulfide cluster Fe4S4. So this is a interesting and non-trivial problem to solve for standard numerical methods. And so you take this molecule and you try to you want to model this system on a realistic basis set. So something that when you talk to your chemist friend, they don't start laughing, right? So something that can really capture the physics of this molecule. So that would be some correlation consistent basis set. But then if you do that, to model this iron sulfide, you would need 72 qubits and 6.7 million Pauli operators. Now, if we wanted to even measure the energy once for this molecule with these 6 million Pauli operators, this will result, using standard VQE techniques, this will result in a runtime of 3 million years even on our quantum processors, which are the superconducting-based quantum processors, which are the fastest ones. So there are methods that people have come up with to improve this overhead, classical shadows and qubit-wise commuting operators and so on and so forth. But those ones will probably shave off a factor 100, 1,000 of these 3 million years. So it seems that fundamentally variational algorithms are very hard to scale up for chemistry. Okay, and so what do we do now? This motivates my talk, and so this motivates why we believe we really need hybrid quantum and classical algorithms to tackle these problems. So these are the three questions that I'll try to address in this talk. The first one is, can we simulate realistic quantum model of nature with the quantum computers that we have now? So before the advent of fault-tolerant quantum computers. And so realistic quantum models of nature is that, the kind of problems that I showed you before, that iron sulfide. The second point is, can we simulate with provable convergence on the quantum computers that we have today? So we would also like to have some kind of algorithm that has the same guarantees of phase estimation or something like that. And the third one is, how does quantum advantage look like within this ground state problem framework? Okay, so I'll try to address these 3 points. The first one, to address the first one, this is a quantum and HPC story. So we collaborated with the RIKEN National Lab in Japan, and so the first experiment I'm going to present was run on our IBM Heron processors. You see here a nice picture of our IBM Quantum System 2, and the supercomputer Fugaku hosted in Kobe, Japan. This first experiment, we did it by a cloud, and so you see that these two systems will interact together. Okay, so what's the idea? How does this work? So how do we go around that measurement problem? This is a simplified picture of the workflow. So what we do is, first we prepare a wave function on a quantum computer, which we believe is a good approximation of that ground state. And once that wave function is prepared, we measure from it. So we extract a set of measurement chi tilde from that quantum computer. And that set of measurement, at this point in the most simple version of this workflow, once we execute the circuit on a quantum computer, there's no feedback, not in this first version of the workflow. So we take those measurements and we send them to classical processing. So the set of measurements chi tilde goes undergoes some error mitigation steps, a part that we call configuration recovery. Basically, you can think of this as trying to statistically undo some of the errors that have happened on that chi tilde measurement set. So it's statistically trying to flip bits in a smart way in that set chi tilde to undo some of the errors that happen. Then we subsample by frequency from that measurement set, and we create a bunch of k batches of measurements, and within each batch of measurements, we project and diagonalize a target system Hamiltonian in a subspace spanned by those measurements. Then at the end, we check which one of these batches gave us the lowest energy, and that's our final solution. And then we can iterate this and go back to the configuration recovery step, which takes as an input average occupancies from this step here. We do this a few times. So what happens here is that now you see that the problem of estimating these molecular energies now shift to a classical compute. And so we don't have to deal with that, normal statistical errors of VQE, right? It's all handled by classical, and it's all done at machine precision. So the only thing that the quantum computing is doing here is providing you with these samples. So it's telling you where in the Hilbert space you have to look to get this ground state. Okay, so why this works so well, I'm going to show you the results in a bit, but I just want to give you a flavor, like a kind of like intuition why this thing works so well. So let's make up a very simple example. This is a ground state that you see down here. It's the ground truth for some system Hamiltonian, which we don't care at this point what's the Hamiltonian, but the only thing that you need to care about is that's the ground state. Okay, and now suppose that I have prepared on my quantum computer an approximation of this ground state with a certain quantum circuit that I have some confidence in will produce this state, and I sample from that quantum circuit, and I get 3 bit strings as an output, right? So A, B, and C. 2 of them are green, 1 is black, and so the green ones, I nailed them, right? So those are exactly the bit strings that I need to recover this ground truth. And the black one, maybe I don't need that one, so maybe that happened because of noise, or maybe because I wasn't smart enough to come up with a good ansatz for this ground truth here. But this is not going to matter, because when I project and diagonalize my target system Hamiltonian in a subspace span by these 3 bit strings, what I'm going to get is a linear combination of those 3 states, which has the lowest energy possible for that system. And so you can guess what that linear combination is going to be. It's going to be that one. So equal weight on A and C, and it's going to assign 0 weight to the faulty bit string B. So now you understand why this works so well, right? So in a way, the classical processing is completely getting rid of quantum errors as long as I have some green signal. So I could have had 1 million more black bit strings. As long as I have the 2 good bit strings, this is going to work perfectly every time. Okay, so what's the catch? The catch is that we are paying a classical price in diagonalizing that system to get the answer. If I have a lot of black bit strings, that classical price scales with the number of black bit strings that I have. It scales polynomially. But still, obviously the number of black bit strings is going to scale exponentially with the noise that I have in my quantum system. So in a way, there's no magic here, but the only thing that's happening is, again, we are trading off classical computational price for how good our quantum computers are, so how many bit strings I'm getting out. Okay, so. And then the last thing, the wave function that we are using to approximate these molecular ground states is this local unitary coupled Jastrow wave function, which is basically, it's something in between unitary coupled cluster ansatz, which is a very chemically motivated is a chemically motivated ansatz, and something like the hardware efficient ansatz. So something in between that, and it's basically interleaved steps of Givens rotations and density-density interaction. So you do that many times, and you can show that there is a value for those angles that recovers the unitary coupled cluster ansatz. And this is what we're using. And so putting all together, this is the results that we got last year. The paper got published this year. So here's three sets of experiments. On the right, you can see we're calculating the dissociation of the nitrogen molecule. And so you see that the quantum computer, in this case, can qualitatively capture this dissociation. And so you see the quantum points here are well aligned with other classical methods. In the center set of experiments, we compute eigenenergies of the iron sulfide Fe2S2, smaller than the one that I showed you at the beginning. And so what we do here is we basically do a scatter plot of the energy variance scatter plot of the points that we get out of the quantum computer. So for each point out of the quantum computer, we compute not only the energy on the y-axis, but also the variance of that energy on the x-axis. Basically, if you do the scatter plot, and so you see the colors here in this plot are the number of measurements that we're using from a quantum computer to do that projection diagonalization step. And you see that as this color gets darker, we're using more measurements, and so this energy gets lower. Right? So this all makes sense. We're using more computational resources, and we get better energies. So within this framework, by the way, lower energy, it's always better. So since there is no normal Gaussian, central limit theorem kind of errors, every energy here is a perfectly representable classical solution, and we can rank these energies without worrying about those statistical errors. So lower energy is better. But then what happens is if the approximation of this ground state is good enough, so if that approximation is really close to the ground state, when you do this energy variance scatter plot, what you'll see is linear arrangement in this scatter plot, that signal that we are sampling to something that's very close to an eigenstate. And so you see for this Fe2S2 molecule, so we see three linear arrangements of those points. And for the last linear arrangement, if we extrapolate that to the point of zero variance, which is what you will get if you had the exact ground state, that extrapolation matches with state-of-the-art DMRG calculation. So this is, I think, this is the best result that we have in terms of accuracy so far. And this is a pretty big system. It's like something like 45 qubits. And then the last set of experiments, we did the Fe4S4 molecule, that 3 million year molecule that I showed you at the beginning. And so here we're really pushing the capabilities of this hybrid hardware and software architecture. And you see that, so we do better than Hartree-Fock state. So the quantum points are the pentagons here. So that's the Hartree-Fock line, but it doesn't look as good as Fe2S2. And so after, I'll show you how we improved on these results this year by doing a feedback loop between quantum and classical supercomputer. Okay, and so this paper got published recently. And so this is just wanted to point out again, these are the runtimes that you will get if you're trying to tackle that Fe4S4 molecule on VQE. It's the 3 million years. We can't really do that. Even if I had a fault-tolerant quantum computer, this will take something like 13 days of runtime and 4 million physical qubits. This is the estimation done with the surface code. So maybe if we use our gross code, the qubit overhead will go down. But nevertheless, it's a non-trivial calculation. And so within this quantum-centric supercomputing framework, using quantum and classical, the doing the energy for this molecule took 2 hours. But this is not a statement about the accuracy of these calculations, but I'm just telling you that we can do these kind of systems right now. So we can play with this kind of systems on the computers that we have today. And so you see that plot that I showed you before. Now, these are the kind of system sizes that we can do if we think of how to use quantum and classical resources together. Okay, so and then what we say, these systems that we're doing, we say that they are beyond exact diagonalization. What we mean is that the kind of system sizes that we are doing are not amenable to classical exact diagonalization methods. So this system that you see in red here, this is the classical state-of-the-art for concerning classical ED methods. And the kind of system sizes that we're doing are well beyond that and well beyond the memory storage of the current supercomputers. Okay, now this year, what we did is we improved on the workflow of last year. So I told you before that all that we were doing is we were taking measurements from a quantum computer, shipping into classical, and do that projection diagonalization step. Now this year, this is still unpublished results. What we do is we close a feedback loop between a quantum computer and the classical supercomputer Fugaku. And so the way that we do it, we work with our architecture infrastructure team. So what happens is, a certain user sends a workflow, a hybrid quantum classical workflow to a workflow manager. And the workflow manager ships quantum and classical parts of the computation optimally. So picks the number of nodes on Fugaku and sends the circuit to the Heron processors in New York. But now the difference is that this is not just a one-way street, but now we get feedback from the supercomputer Fugaku, and we send the energy back so that we can improve the angles of the approximate wave function that we are considering. And so this, see, we get results at the end. And let's finish. So using this kind of more complex workflows, so this is a description of the workflow. What we use is a differential evolution optimizer. We use this kind of workflow because, so in this optimizer, we have two populations. We don't want to have the supercomputer or the quantum computer idle at any time because these are very expensive machines. So what we have, so we don't want the supercomputer to wait for the quantum computer to finish its calculation and vice versa. So what we have is an optimizer with two populations going on. So when the classical energy is computed on the supercomputer, the quantum computer is running the circuit for the other population and vice versa. And so you see here, this is the usage of the Fugaku, supercomputer Fugaku, and the quantum computer Marrakesh. So the white parts here are the idle times, so it's not perfect, but you see that we are using quantum and classical together. And so with this kind of improved workflow, this is the energy that we got this year. So this is unpublished results. We used more determinants in the diagonalization, and you see that on the x-axis here, this is the iterations going on between quantum and classical processors, right? So you see that's what I showed you before, the best result that we got last year, and this is the new energy this year. Yeah, we are not doing better than state-of-the-art classical methods yet, but you see that how things are improving if we consider more complex workflows. Okay, now. The other question is, okay, now we can do these molecular systems of large size. And then the other question is, can we simulate things with provable convergence before fault-tolerant quantum computers? So I also want something that behaves like phase estimation, but I want to do it on the quantum hardware that we have today. All right, the idea is this credo of quantum diagonalization idea, right? So how do we do it? So in this time, instead of sampling from a quantum computer and projecting and diagonalize in the measurement subspace. What we do is we prepare quantum states that are time-evolved quantum states. With some power, we do these time evolutions with some power d, from 1 to d, and then we estimate matrix elements of the Hamiltonian and the overlap matrix between these states, because now these are non-orthogonal states. And we classically solve this generalized eigenvalue problem. So you can show, if you do that, this algorithm as a convergence, which is reminiscent of phase estimation. So this is the energy error that we get as a function of the Krylov subspace size D, which is how many powers we use of that real state time evolution. You see there are other parameters, and so you see there is a part of this error which has an exponential decay in D. So this is also similar to what you get with a classical Krylov algorithm, like Lanczos or Arnoldi methods and those ones. But there is a new term that appears, which has the gap of the system and also eta, parameter eta. And now eta, this is something that shows up when we do things on a quantum computer. So eta is how good we can approximate these matrix elements. In the quantum computer, we have statistical errors, and we have decoherence, so on and so forth. So eta, that's where it comes from. So this is a new part. And then at the denominator here, you see gamma 0, which is the overlap of our reference state with the final ground state. And so this is the part which is like phase estimation. So we did an experiment together with University of Tokyo, and so we see that indeed, even experimentally, we kind of like see that behavior. This is a Heisenberg model, and this is the energy that we get for that Heisenberg ground state in different number of excitation sectors as a function of the subspace dimension D for that Krylov subspace. And so you see that that's the behavior that you get. So there's an exponential decay, and then things get saturated because of that term, eta, over there. But nevertheless, here, there's no need to come up with an ansatz anymore, right? So we've overcome that problem. So this is something that looks like phase estimation, but something we can run on the computers that we have today. Then the natural thing to do is we put together these two ideas. So now I want to go around the issue of estimating those matrix elements with the error eta, right? And so what we can do is we can still prepare the powers of this unitary evolution of your target system, but this time we don't statistically estimate those matrix elements, but we sample from a quantum computer from those states, and then we project and diagonalize in a subspace spanned by those samples. And again, you can prove that there is guaranteed convergence for this workflow, so the real state evolution plus sampling, for if your ground state is sparse. Right? And so this is the total number of shots that you need, basically the runtime, as a function of the final energy error, and again, eta, and eta, this is another eta here. And then gamma 0, which is the overlap with our ground state. We did an experiment this time. We collaborated with Oak Ridge, and we did an experiment with our quantum processors and the supercomputer Frontier at Oak Ridge. And we tackled the single impurity Anderson model. Actually, in the updated version, we did many impurities. And you see here the agreement of this method, which we call sample-based Krylov quantum diagonalization with state-of-the-art DMRG calculations. It's pretty good. And so this is the correlation functions computed over the ground state for that system. Okay, and then just I want to advertise a poster by Samuele, which was being presented yesterday, right? But so here, what we're doing in this paper is now we're saying, okay, but I cannot really run these Krylov business for chemistry because the depths that I need to do those time evolutions for chemistry is too large. And so what we do is we combine this idea of like Q drift, so probabilistically sample from the Hamiltonian terms in that time evolution and the Krylov subspace ideas. And so this allows us to do chemistry with provable convergence on the computers that we have, pre-Fultonian quantum computers. Again, talk to Samuele if you want to know more about this paper. All right, then finally, how does quantum advantage look like within this framework? So imagine that this rectangle here is your full Hilbert space, and the red circle is the determinants that we need, the configurations that we need to get that ground state, right? Then imagine that there is some classical method, which is the blue circle here, that captures some of those states, but not all of them, and just other states that we don't care about, right? And now imagine that there is a quantum method, which is the yellow circle, that captures all the states that the classical method gives me, and then some more. Okay, and then for sure, the ground state that we get out of the yellow circle is going to be better than what we get out of the blue circle. So this is one type of quantum advantage that could emerge out of this framework. The second type is, so just we find new samples that we cannot find with classical. The second type is a sample efficiency. So this is the FE2 system that I showed you before, energy on the y-axis, subspace dimension on the x-axis. So what we are doing here is we are comparing a classical method, which is the purple dots. The steps of this classical method, this is a classical selected CI method based on heat path. And so what this method is doing is producing configurations that I can diagonalize my system against, and it's doing it iteratively. So every time that I run this SCI method, it gets better. It gives me new samples, and the energy gets lower. But then one question that one can ask is this classical method producing the best samples for a given subspace size? Meaning if I fix my subspace size at 50 million here, is this classical method giving me the best 50 million determinants that possible? And the answer is no. So this is a calculation that we did brute force, but we found better 50 million determinants that this classical method was giving us. And this is the brown line here. So the answer is these classical SCI methods, they're not saturating sampling efficiency. So we can do better than these methods. And then the second thing that we did, now we took a short depth quantum circuit, one of those LUCJ circuits, and we, again, brute force calculation, but we tuned the parameters of that circuit so that it could sample very close to the brown line. And we found those parameters. So the bottom line is that there exist quantum circuits that can sample more efficiently than SCI methods. We have to find them. We have to find them efficiently, but they exist. All right, and so last couple of slides that I have, I'd like to advertise the work that we are doing with our industry partners. So these techniques got a lot of interest from industry players like Cleveland Clinic, Lockheed Martin, Boeing, so on and so forth. And also, I also want to advertise that if you have interesting ideas, experiments that you want to run on the IBM quantum devices, please reach out to us. So we're here, talk to us. We can figure out ways of giving you access to the quantum devices that we have to run your experiments. Okay, so thank you all for your attention. That was my last slide. Thanks.
All right, questions?